In real-world environments, it is difficult to create a robot that is optimal in all situations. For example, wheeled robots are cheap and effective for most tasks, but they fail when they encounter difficult terrain such as small spaces or stairs. There are more complex and biologically inspired robots, such as snake-like robots, which are more capable of traversing through tough environments, but they are often limited to power and computing payloads. Novel strategies for autonomous, snake-like locomotion through complex environments are difficult to evaluate due to the use of tethers, which deliver power and communication but restricts the size of experimental scenarios. This project leverages a Turtlebot to serve as an autonomous mobile workstation, which is capable of providing computational and electrical power to the robotic snake, thus permitting algorithms for the snake-like locomotion to be evaluated experimentally over larger regions. In previous setups, the robotic snake was limited to a stationary workstation. From the power supply shown on the right, the tether connects to the robotic snake. However, due to the limited length of the tether, locomotive strategies cannot be thoroughly tested over larger expanses of terrain.
The robotic snake is an in-house developed robot derived from 10 linked dynamixel motors, which are housed in 3D printed scales to provide locomotive friction as it traverses along the ground. The robotic snake is typically attached to a computer via a tether, which provides power and motor commands. This tether is a physical restriction that limits locomotive strategies. In the image, the robotic snake is shown in the top. Instead of being attached to a stationary computer, the tether is attached to the Turtlebot as a mobile workstation for increased flexibility. The Turtlebot is a differential drive vehicle, meaning that it can only move forward and turn in place. It is built off of the popular Kabuki base, similar to that of a Roomba vacuum. We initially attached a Logitech C920 webcam capable of color sensing and progressed to the Intel RealSense D435i camera capable of color and depth sensing. The purpose of the Turtlebot is to act as a mobile workstation by following the robotic snake and providing power and motor commands. In the image, the Turtlebot is shown in the bottom. It is controlled via the attached laptop, contains a built-in battery, and houses an adapter to control the robotic snake. Even though the leader follower robotic system does not consist of a typical stationary workstation, there still exists a command center, the Turtlebot. As the mobile command center, the Turtlebot is responsible for assigning itself and the robotic snake appropriate commands. First, the Turtlebot sends out motor commands to the robotic snake to follow one of several motion primitives. Upon receiving these motor positions via the tether, the robotic snake's motors are updated and motion pursues. The Turtlebot is tasked to follow the robotic snake as it travels. The Turtlebot uses an onboard camera to determine the robotic snake's location within the environment. Input from a continuous image feed allows the Turtlebot to quickly update its orientation relative to that of the robotic snake, in doing so, keeping the robotic snake centered in its frame. Additional tasks such as localization and mapping will be performed by the Turtlebot.
The snake travels through two gate primitives, the first being sidewinding. This involves propagating a sine wave through the body of the snake with a sliding ground contact pattern and results in a movement that is analogous to bipedal locomotion. The dynamic model of this gate is simplified to a kinematic one, where the average body velocity of the snake can be controlled by modulating the gate's parameters, such as amplitude or wavelength. This dynamic model also allows for steering by adding a curvature to the average body of the snake, but results in testing for inconsistent. This may be due to the lengths of the snake being too long to accurately reproduce the continuous curve, or an incorrect implementation of it. Due to this problem, sidewinding is only used for linear movement. To control the orientation of the snake, a turn-in-place gate is used. This uses a two-part gate cycle that results in the snake rotating with minimal translational motion. In this way, the snake is controlled using two types of movement for both linear and rotational motion.
The purpose of tracking the robotic snake is the ability to keep the mobile command center within close proximity, therefore eliminating tether constraints previously imposed by tethering to its stationary workstation. The Turtlebot with its onboard camera seeks to maintain a specified distance from the robotic snake while keeping it in the center of the camera frame. In order to segment the robotic snake from its environment, magenta markers have been placed on each scale. By increasing the saturation setting of the camera, these markers are distinct enough to isolate the robotic snake, shown in the left image. Creating a color model to accept a range of values consistent with those of the magenta markers allows a mask to be created of the environment, shown on the right image. This mask isolates the robotic snake's markers. From this mask, the centroid is calculated and is used as the position of the robotic snake relative to that of the turtlebot. The intersection of the vertical and horizontal white lines indicates the desired position of the centroid. By tuning PID gains for both the linear velocity and angular velocity control laws, the turtlebot is able to correct its position and orientation relative to the robotic snake's center.
The Open Motion Planning Library, also known as OMPL, is used to plan paths for both the turtlebot and the robotic snake between a specified start and end position. The purpose of this library is to provide a path planning algorithm. This planning library allows the turtlebot to find the shortest and most efficient path between the start and end position. Essentially, this library allows the user to input multiple waypoints between the start and end position. With these waypoints, the turtlebot will be able to find the most optimized path. Below is an example environment used to test the Open Motion Planning Library with predefined points and the obstacles between the start and end positions.
For our initial scenario, we set out to show the performance of the robotic snake's sidewinding capability and the ability of the turtlebot to successfully track the snake. Using the magenta markers placed on the snake's scales, the turtlebot is able to differentiate the robotic snake from its environment. Looking at the images on the left, initially the robotic snake is placed 3 feet in front of the turtlebot, as this is a specified following distance. In the next image, as the robotic snake performs straight average body sidewinding, it progresses through the environment at about 1 foot every 5 seconds per gait cycle. The turtlebot, using its forward-facing camera, is able to compare the changing pose of the robotic snake's centroid to a specified reference pose. This allows the turtlebot to adjust its forward and angular velocity and maintain a fixed distance and orientation behind the robotic snake. In image 3, as both robots move through the environment, the turtlebot remains approximately 3 feet behind the snake. In the last image, as the robotic snake reaches its final position at the boundary of the scenario environment, it comes to a halt. The turtlebot follows suit by slowly reducing its velocity and stopping behind the robotic snake. As we have demonstrated in our scenario, we have successfully implemented a tracking system, allowing the turtlebot to follow the robotic snake at a specified distance while keeping it in its center view. We have also implemented the sidewinding motion controller, which allows the turtlebot to control the snake. And finally, we have started working with OMPL and testing a virtual environment using it. In the future, we would like to do further testing with the sidewinding gate to more accurately control steering. One potential method would be to add a linear envelope to the amplitude of the sine wave of the gate instead of modulating average body curvature. Next, we would like to integrate tracking and following and path planning with OMPL and verify gate control to accomplish robotic snake, turtlebot, leading, following.